November 5, 1941, 12:03 p.m. The Los Angeles sky cloudless and bright as Lockheed test pilot Ralph Verdun pushed his P-38 Lightning into a steep power dive from 25,000 feet. The twin Allison engines screaming as the airspeed indicator climbed past 350 miles per hour, past 400, the airframe beginning to shake as he descended through 18,000 feet. And suddenly the nightmare began. Shock waves forming invisibly over the wing roots as the airflow accelerated past the speed of sound, the center of lift lurching backward toward the tail, the nose pitching violently downward into an uncontrollable tuck, the control column frozen solid in Verdun's hands despite his desperate pulling, and then the catastrophic structural failure, the tail assembly simply separating from the aircraft, floating away like a discarded piece of paper, while 25,000 Lockheed employees gathered for an outdoor luncheon celebration below watched in horror as the mutilated fighter tumbled from the sky, trailing smoke and fire, crashing into a residential neighborhood in Glendale, trapping Verdun in the burning wreckage where homeowner Jack Jensen tried frantically to pull him free but was driven back by flames, the screaming and the heat, the smell of aviation fuel and burning metal, and within minutes Ralph Verdun was dead, the best dive pilot Lockheed had, killed by a phenomenon that almost nobody understood, a problem that had been predicted 3 years earlier by a 23-year-old engineer whose warnings had been largely ignored, a deadly flaw that would kill dozens more pilots in training and combat before a solution could be found, tested, and deployed. And that solution, when it finally came, would be so simple, so elegant, so effective, that it would transform the P-38 from a dangerous liability into an untouchable predator. But the path to that solution would be blocked by bureaucratic timidity, institutional caution, tragic accidents, and the kind of infuriating delays that cost lives in wartime. The story of how a small, hinged panel measuring roughly 2 feet long and mounted under each wing saved the P-38 Lightning and revolutionized high-speed aerodynamics begins not in 1941 with Verdun's death, but in 1937, when a young Lockheed engineer named Clarence Leonard Kelly Johnson, who had joined the company fresh from the University of Michigan's Aeronautical Engineering program in 1933, who had immediately made his mark by solving wind tunnel interference problems that were showing the company's Model 10 Electra was unstable when it actually flew perfectly, who, at age 23, had more confidence than political sense, submitted a report to the Army Air Corps, warning that the experimental XP-38 fighter his team was designing would almost certainly encounter compressibility effects at high speeds and high altitudes, phenomena that were barely understood theoretically and had never been observed in actual flight because no aircraft had ever flown fast enough. Johnson understood the basic physics, knew that as an aircraft approached the speed of sound, air molecules could not move out of the way fast enough, and would compress, forming shock waves, but predicting exactly what would happen when those shock waves formed over a wing or tail surface was largely guesswork in 1937. And the Army Air Corps, faced with Johnson's dire predictions about a problem that had never actually occurred, chose to proceed with development, gambling that either the predictions were overly cautious or that solutions could be found if problems emerged. The gamble seemed reasonable because the P-38's design was revolutionary in every respect, a twin-engine fighter with counter-rotating propellers to eliminate torque, with engines mounted in distinctive twin booms that also housed the main landing gear and radiators, with a central nacelle containing the pilot and an unprecedented nose-mounted armament battery of 450 caliber machine guns and one 20mm cannon, all firing straight ahead without convergence angles, creating a cone of destruction at ranges up to 1,000 yards. The Air Corps desperately needed this aircraft. Specifications had been issued in 1937 calling for a high-altitude interceptor capable of 360 miles per hour at 20,000 feet with heavy armament, and Lockheed's design, radical as it was, promised to exceed every requirement. Company founder Hall Hibbard and Chief Engineer Johnson working together to create what would become one of the war's most distinctive fighters. The prototype XP-38 first flew on January 27, 1939, flown by test pilot Ben Kelsey, and the aircraft's performance was immediately spectacular, so impressive that the Air Corps arranged a transcontinental speed record attempt to generate publicity, and on February 11, 1939, Kelsey departed March Field in California for Mitchell Field in New York, making the crossing in 7 hours and 2 minutes, including refueling stops, smashing the previous record. But then, while approaching Mitchell Field for the final landing, both engines quit due to fuel exhaustion from a misunderstood fuel system configuration, and Kelsey crash-landed on a golf course, destroying the prototype but walking away alive. Despite losing the only prototype, the Air Corps was sufficiently impressed to order 13 YP-38 service test aircraft in April 1939, and these pre-production fighters began flying in 1940, and it was during high-speed dive testing of the YP-38s that the compressibility problem Kelly Johnson had warned about 3 years earlier revealed itself with terrifying clarity. Pilots reported that during dives above approximately 350 miles per hour indicated airspeed, the aircraft would suddenly pitch nose down into an uncontrollable tuck, the elevator becoming completely ineffective, the control column frozen by aerodynamic forces far exceeding human strength, and the only recovery technique was to throttle back, extend the landing gear and flaps to add drag, and pray that the aircraft would slow below the critical speed before running out of altitude. The problem was not just academic or theoretical. This was killing pilots, and Ralph Verden's death in November 1941 was simply the most visible casualty, the crash occurring in daylight over Los Angeles, where thousands witnessed the disaster, but training accidents at remote bases, classified operational losses, these were adding up, and confidence in the P-38 among pilots was eroding, even as production ramped up for the war everyone knew was coming. Kelly Johnson and his engineering team at Lockheed understood they faced an existential crisis. The Air Corps had ordered thousands of P-38s. The production lines were running at full capacity, but the aircraft had a potentially fatal flaw, and if word spread that the Lightning was killing its own pilots, the entire program could be cancelled, tens of thousands of jobs lost, America's war effort crippled. Johnson's team conducted extensive analysis, flight testing, and theoretical studies, gradually piecing together what was happening during high-speed dives, the shock waves forming over the wing's leading edges when local airflow exceeded the speed of sound, typically around Mach 0.68 for the P-38, these shock waves causing airflow separation and a sudden loss of lift on the inboard wing sections. Simultaneously, the center of pressure on the wing moving dramatically rearward toward the tail, creating a powerful nose-down pitching moment that overwhelmed the elevator's authority. The technical challenge was unprecedented. The P-38 was encountering aerodynamic phenomena that had never been observed in flight, that were poorly understood theoretically, and that required research tools and facilities that barely existed. Johnson knew that solving the problem properly would require extensive wind tunnel testing at transonic speeds, conditions where the airflow over the model would approach or exceed the speed of sound. But in 1941, there were exactly 2 wind tunnels in America capable of such testing, both operated by the National Advisory Committee for Aeronautics, the government research organization that would later become NASA, one at Langley in Virginia, that could reach speeds of only 100 miles per hour, useless for this purpose, and a newer, smaller tunnel at the Ames Aeronautical Laboratory in California that could theoretically reach 250 miles per hour, still less than half the speed needed to properly investigate compressibility effects. In early 1942, with America now at war following Pearl Harbor, with P-38s rolling off production lines and being rushed into service, with pilots dying in training accidents, Kelly Johnson formally requested that NACA modify their Ames wind tunnel to reach the higher speeds necessary to conduct proper testing of the P-38's compressibility problems. The response from NACA was bureaucratically cautious and militarily catastrophic. The agency's leadership refused Johnson's request, arguing that running the tunnel at higher speeds would risk damaging the facility, that the tunnel was a national research asset that could not be jeopardized, that alternative approaches should be explored. Johnson's frustration was palpable. Here was Lockheed, a private company, designing and building advanced fighters for the war effort, encountering a fundamental aerodynamic problem, asking to use government research facilities that had been built with taxpayer money specifically to support the aviation industry, and being told no because the government scientists were afraid of breaking their equipment. The institutional failure was profound and consequential. NACA had been established in 1915 specifically to advance American aviation through research and development. The agency had produced valuable work in the 1920s and 1930s, including the engine cowling that revolutionized aircraft design. But now, when confronted with an urgent wartime requirement, when American pilots were dying because an aircraft had encountered conditions beyond existing understanding, NACA's response was to protect their facilities rather than solve the problem. The impasse lasted for months, Lockheed continuing to build and deliver P-38s with the known compressibility flaw, the Army Air Forces accepting aircraft that had handling limitations documented in pilots' manuals, warnings that high-speed dives above certain altitudes could result in loss of control, procedures for recovery that amounted to hoping the aircraft would slow down before hitting the ground. It took intervention from the very top of the military hierarchy to break the bureaucratic logjam. General Henry Hap Arnold, commanding general of the Army Air Forces, who understood that America desperately needed long-range fighters and that the P-38 was the only aircraft that could fill that role, personally ordered NACA to conduct the high-speed wind tunnel tests Lockheed had requested, essentially commanding the research agency to accept the risk to their facilities because the war effort demanded answers. The order came in late 1942, more than a year after Ralph Verden's death, more than a year during which pilots continued dying or narrowly escaping death due to compressibility, and even after Arnold's order, it took additional months to modify the Ames tunnel, install the P-38 model, and begin generating data. The wind tunnel tests conducted in early 1943 at Ames finally provided empirical data about what was happening to the P-38 during high-speed dives, confirming Johnson's theoretical predictions from 6 years earlier, showing clearly how shock waves formed over the wing leading edges, how the center of pressure moved aft, how airflow over the wings separated, reducing downwash at the tail and rendering the elevator ineffective. But understanding the problem was only the first step. Actually solving it proved even more challenging because the fundamental issue was the wing's aerodynamic design, and redesigning the wing would require essentially creating a new aircraft, halting production, retooling factories, losing months or years of production, completely unacceptable during wartime when aircraft were needed immediately. Kelly Johnson and his engineering team needed a solution that could be implemented without major airframe changes, something that could be retrofitted to existing aircraft and incorporated into production without shutting down assembly lines. And the solution they developed demonstrated the kind of innovative thinking that emerges when brilliant engineers face impossible constraints. The concept was elegantly simple. Instead of eliminating the shock waves or preventing the center of pressure from moving aft, Johnson's team would install small flaps under each wing, positioned just outboard of the engine nacelles, that could be deployed during high-speed dives to shift the center of pressure forward, restoring elevator authority and allowing pilots to maintain control. The flaps, which became known as dive recovery flaps or dive brakes, were not aerodynamic brakes in the traditional sense. They did not primarily function by adding drag to slow the aircraft. Instead, they modified the pressure distribution over the wing, creating a localized disturbance in the airflow that prevented shock wave formation and kept the center of pressure in its normal position. The theoretical concept was one thing. Proving it would work in the brutal reality of transonic flight was something else entirely, and that responsibility fell to two men, who would risk their lives repeatedly testing the dive recovery flaps, Tony Levier and Milo Burcham, Lockheed's chief engineering test pilots. Anthony "Tony" Levier had joined Lockheed in 1941 after establishing himself as an air racer, winning the 1940 and 1941 Grieve Trophy races, demonstrating the kind of flying skill and judgment that made him invaluable for dangerous test work. and his job was to take experimental modifications and determine whether they actually worked or would kill whoever tried to use them. Milo Burcham, older and more experienced, had joined Lockheed in the late 1930s and had flown more P-38 test flights than any other pilot, accumulating an intimate understanding of the aircraft's handling characteristics and limitations, knowing exactly how the Lightning behaved at the edge of its performance envelope. Beginning in February 1943, Levier and Burcham began a systematic test program, flying P-38s modified with prototype dive recovery flaps, climbing to 35,000 feet, rolling inverted, pulling through into vertical dives, accelerating to speeds that had previously resulted in fatal loss of control, then activating the dive flaps and observing the results. The tests were extraordinarily dangerous. Each dive represented a calculated risk that the flaps would not work as designed, that the aircraft would enter an uncontrollable tuck, that recovery would be impossible, that the test pilot would have seconds to decide whether to ride the aircraft down or attempt to bail out from a violently maneuvering fighter at terminal velocity. But the dive recovery flaps worked, better than Johnson's team had dared hope, the small panels deploying to 35 degrees in approximately 1.5 seconds when activated by an electrical switch in the cockpit, immediately restoring elevator effectiveness, allowing pilots to pull out of dives that would have been fatal without the modification. Levier's test reports documented systematic improvements, showing that P-38s equipped with dive recovery flaps could maintain controlled flight at significantly higher speeds than unmodified aircraft, that pilots could pursue enemy fighters through any dive maneuver without fear of losing control, that the modification transformed the Lightning's tactical capability. The success of the testing program led to approval for production implementation in late 1943, with dive recovery flaps to be installed on the P-38J-25 variant and all subsequent production aircraft, and retrofit kits to be manufactured for earlier P-38s already in service. The production plan called for over 200 modification kits to be shipped to England for installation on P-38s serving with the 8th Air Force, which desperately needed the capability because German pilots had learned to exploit the Lightning's compressibility weakness, diving away whenever engaged at high altitude, knowing that P-38 pilots could not follow without risking loss of control. In March 1944, those 200 desperately needed retrofit kits were loaded aboard a Douglas C-54 transport for flight to England, and the aircraft took off from the United States, carrying what amounted to months of production work and the solution to a problem that had been killing Allied pilots for 3 years. The C-54 never reached England. On March 19, 1944, while approaching the British coast, the Douglas transport was intercepted by a Royal Air Force fighter pilot who misidentified the 4-engine aircraft as a German Focke-Wulf FW-200 Condor, opened fire and shot down the American transport, killing the crew and destroying the cargo, including all 200 dive flap modification kits. The friendly fire incident was a tragedy compounded by terrible timing. P-38 units in England had been briefed that the dive flap modifications were coming. Pilots were expecting the retrofit kits that would finally allow them to compete on equal terms with German fighters at high altitude, and instead they learned that months of production had been destroyed, that replacement kits would have to be manufactured, that the wait would continue. Kelly Johnson, learning of the loss, estimated that the destruction of those kits and the resulting delay cost over 300 American aircraft and their crews, pilots who died because their P-38s lacked the capability to pursue diving enemy fighters, missions that failed because German pilots simply dove away whenever engaged, the cumulative cost of a single identification error by an RAF pilot who shot down the wrong aircraft. The loss of the retrofit kits meant that P-38s already deployed in Europe would not receive dive recovery flaps for additional months, not until new kits could be manufactured and shipped via safer routes. And in the meantime, pilots continued flying with the original limitations, continued breaking off pursuit when German fighters dove, continued losing the psychological advantage that aerial dominance requires. The P-38J-25 variant, the first Lightning to be built with dive recovery flaps installed on the production line, rather than retrofitted in the field, began reaching combat units in Europe in spring and summer 1944, more than 3 years after Ralph Verden's fatal crash, more than 2 years after Kelly Johnson first requested NACA wind tunnel testing, 14 months after Levier and Bertram proved the flaps worked in testing. The impact in combat was immediate and dramatic. P-38 pilots who had spent months watching German fighters escape by diving suddenly discovered they could follow their targets through any maneuver, could press attacks that had previously been impossible, could exploit the Lightning's superior firepower and high-altitude performance without fear of losing control. Lieutenant Colonel J.T. Robbins, commanding the 82nd Fighter Group flying P-38s from Italy, reported that dive recovery flaps fundamentally changed the tactical situation. German pilots who had routinely evaded by diving were now being caught and destroyed. Kill ratios improved dramatically. Pilot confidence soared. The 15th Air Force's 3 P-38 fighter groups based in Italy, the 1st, 14th and 82nd, saw their combat effectiveness transform after receiving dive flap modifications, kill ratios improving from barely 1-to-1 in early 1944 to nearly 4-to-1 by September, as pilots exploited their newfound capability. In the European theatre, where high-altitude combat was routine, and German pilots had long exploited the P-38's compressibility weakness, the dive recovery flaps eliminated a tactical disadvantage that had cost lives and missions. The modification's impact extended beyond immediate combat effectiveness to psychological and operational factors. P-38 pilots who had approached missions with the knowledge that their aircraft had a potentially fatal limitation now flew with full confidence, pressing attacks aggressively, pursuing targets through any escape maneuver, and German pilots who had relied on diving tactics to evade P-38s discovered that their proven escape technique no longer worked. The intelligence reports from interrogated German pilots revealed their surprise and frustration. Luftwaffe fighter pilots who had survived combat against P-38s for months by diving away suddenly found themselves being pursued, taking fire during dives they had assumed would be safe, discovering that the Americans had somehow solved the Lightning's notorious handling problem. Some German pilots initially assumed they were facing a completely new American fighter design, unaware that the transformed capability came from a relatively simple modification involving small hinged panels under the wings. The dive recovery flaps exemplified a distinctly American approach to wartime problem-solving, when confronted with a fundamental aerodynamic limitation, rather than accepting reduced capability or designing an entirely new aircraft. Engineers developed an incremental modification that solved the specific problem while maintaining production continuity. The contrast with German approaches to technical problems was stark. Germany invested enormous resources in revolutionary technologies like jet fighters and swept-wing research, pursuing fundamental breakthroughs, while America focused on practical improvements to existing designs, modifications that could be implemented quickly and deployed to combat units within months rather than years. Tony Levier's role in proving the dive recovery flaps went beyond test flying. In early 1944, he was sent to England specifically to demonstrate the modification's capability to skeptical P-38 pilots who had heard promises before and learned not to trust engineering solutions until proven in front of their eyes. At RAF Kingscliff, home of the 20th Fighter Group flying P-38s, Levier gave a technical briefing describing the compressibility problem and explaining how the dive recovery flaps solved it, and the assembled pilots listened with the polite skepticism of combat veterans who had watched friends die and who were not impressed by theoretical explanations from factory test pilots. Then Levier walked out to his P-38, modified with the dive recovery flaps, climbed to 25,000 feet, rolled inverted, pulled through into a vertical dive directly toward the airfield, accelerating past 450 miles per hour, speed that would normally result in complete loss of control, and the pilots on the ground rushed out expecting to witness a crash, knowing that no P-38 could recover from such a dive. But Levier deployed the dive recovery flaps, maintained full control, pulled out smoothly at low altitude, then, for emphasis, performed several rolls on one engine, demonstrating the kind of aggressive flying that had previously been impossible, and the assembled pilots understood that the modification was real, that their aircraft would soon receive the same capability, that the tactical situation was about to change fundamentally. Levier repeated this demonstration at multiple bases throughout England and Italy, conducting test flights and training sessions that transformed pilot attitudes from skepticism to enthusiasm, and his willingness to repeatedly risk his life performing high-speed dives convinced combat pilots that the dive recovery flaps were not just theoretical improvements, but practical modifications that worked reliably under the most demanding conditions. Milo Bersham, Levier's colleague who had alternated dive testing duties during the development program, would not live to see the dive recovery flaps fully vindicated in combat on October 20, 1944, while conducting a test flight of the experimental XP-80 jet fighter at Lockheed's Burbank facility. Bercham's aircraft suffered an engine failure on takeoff. He attempted to return to the field, but crashed short of the runway, dying in the wreckage, another test pilot killed pushing the boundaries of aviation technology. Bercham's death illustrated the constant danger that test pilots faced, not just during exotic high-speed dives or experimental maneuvers, but during routine testing of new aircraft, and his contribution to solving the P-38's compressibility problem represented just one chapter in a career spent evaluating dangerous prototypes and proving modifications under conditions where failure meant death. The broader impact of the P-38 dive recovery flap program extended far beyond the immediate tactical improvements. The research data generated during the wind tunnel testing and flight evaluations contributed significantly to understanding transonic aerodynamics, phenomena that would be crucial for designing aircraft capable of supersonic flight. The P-38 was among the first aircraft to encounter compressibility effects in routine operations, the first fighter to require modifications specifically to address transonic handling, and the engineering solutions developed for the Lightning helped establish fundamental principles about shockwave formation, pressure distribution, and control effectiveness at high speeds. Kelly Johnson, who had warned about compressibility in 1937, when almost nobody understood what he was describing, who had fought bureaucratic resistance to get the research facilities needed to investigate the problem, who had developed the elegantly simple dive flap solution, would go on to lead Lockheed's legendary Skunk Works, designing the U-2 spy plane, the SR-71 Blackbird, and other revolutionary aircraft. The institutional lessons from the P-38 compressibility saga were profound and disturbing. NSEA's refusal to conduct high-speed wind tunnel testing in 1942 despite urgent requests from Lockheed represented a failure of mission. At a critical moment, the research agency that existed specifically to support American aviation had prioritized protecting their facilities over solving a problem that was killing pilots. The delay cost lives, cost missions, cost tactical advantage, and only direct intervention from General Arnold forced NACA to do the testing that should have been their obvious priority. The friendly fire incident that destroyed 200 retrofit kits highlighted the chaos and confusion of wartime operations, where identification errors and communication failures could have strategic consequences, where months of engineering work and irreplaceable equipment could be destroyed in seconds by a pilot who made a split-second mistake. The 14-month delay between proving the dive recovery flaps worked in testing and getting them into production and deployed to combat units illustrated the complexity of wartime manufacturing and logistics, the challenge of implementing modifications while maintaining production continuity, the inevitable time lag between solving a problem and fielding the solution. Every delay, every bureaucratic obstacle, every shipping problem had consequences measured in dead pilots and lost aircraft, and Kelly Johnson's estimate that earlier implementation could have saved 300 aircraft and their crews was not speculation, but a calculation based on combat loss rates and tactical effectiveness reports. The combat statistics told the story of transformation clearly. P-38 units equipped with dive recovery flaps showed immediate and sustained improvements in kill ratios, mission success rates, and pilot confidence. German escape rates through diving maneuvers dropped dramatically once flap-equipped Lightnings arrived in theatre, while P-38 victory rates increased correspondingly. The modification saved numerous American pilots from compressibility-related losses. Pilots who had previously broken off pursuits rather than risk losing control could now follow enemy aircraft through any maneuver, pressing attacks to completion. The psychological impact exceeded the purely tactical advantages. Knowing that their aircraft would not betray them during high-speed dives allowed P-38 pilots to exploit the Lightning's considerable strengths: heavy, nose-mounted armament, long range, twin-engine reliability, high-altitude performance. In the Pacific theater, where the P-38 achieved its greatest success and produced America's top aces, including Major Richard Bong with 40 victories and Major Thomas Maguire with 38 victories, compressibility was less of a factor, because most combat occurred at lower altitudes where shock waves were less likely to form. But even in the Pacific dive recovery flaps provided tactical advantages and improved pilot confidence. Major Bong flew most of his combat missions before receiving flap-equipped aircraft, his success demonstrating that skilled pilots could work around the P-38's limitations through tactical discipline. But later, Pacific aces benefited from the modification, able to pursue Japanese fighters through any escape maneuver. The production statistics revealed how long the problem persisted. Lockheed built approximately 10,000 P-38s during the war, but only the final P-38J-25 variant and subsequent models received dive recovery flaps as standard equipment, meaning that thousands of earlier Lightnings were delivered with known handling limitations. The retrofit program eventually modified many of these earlier aircraft field modification units, installing dive recovery flap kits in combat theaters. But the process took time, and some P-38s flew through the entire war without receiving the modification. The contrast between the slow, bureaucratic process of implementing the dive recovery flaps and the urgent demands of combat operations illustrated fundamental tensions in wartime acquisition and development. Engineers and test pilots working as fast as humanly possible, while production managers, logistics officers, and military administrators created delays through caution, procedures, and competing priorities. The cost of these delays was not abstract. Every month without dive recovery flaps meant pilots died who could have been saved, missions failed that could have succeeded, tactical advantages lost that could have been exploited. The fact that a solution existed, had been tested, had been proven effective, but could not be fielded for more than a year due to production scheduling, shipping delays, and a catastrophic friendly fire incident represented the kind of institutional failure that retrospective analysis can identify, but wartime participants could do little to prevent. The P-38's ultimate legacy in aviation history is complex and multifaceted. The aircraft was revolutionary in design, distinctively beautiful or strange depending on perspective, tactically valuable but never perfect. And the compressibility problem that killed Ralph Virden and dozens of others represented a fundamental limitation that could only be partially solved. Even with dive recovery flaps, the P-38 could not completely escape the constraints of transonic aerodynamics. The modification restored control authority and prevented catastrophic loss of control, but did not eliminate compressibility effects entirely. Pilots still had to be aware of speed limitations and understand their aircraft's handling characteristics at high speeds. The dive recovery flaps represented a successful engineering compromise, solving the most dangerous aspects of the compressibility problem without requiring a complete redesign, allowing the P-38 to remain in production and service while providing improved capability. The broader aerodynamic lessons learned from the P-38 program influenced post-war fighter design. Engineers understanding that transonic handling had to be considered from the beginning rather than solved after problems emerged, that wind tunnel testing at high speeds was essential, that control systems needed sufficient authority to overcome aerodynamic forces at maximum performance. The experience with dive recovery flaps, small surfaces that modified airflow to prevent shockwave formation, presaged later developments including vortex generators and boundary layer control devices that would become standard features on high-performance aircraft. The human dimension of the P-38 compressibility story extends beyond the test pilots and combat aviators to the engineers who worked endless hours developing solutions, the production workers who built modification kits, the maintenance crews who installed them under field conditions, and the families of pilots who died before the solution could be fielded. Ralph Virden's widow and son, who watched Lockheed management and fellow pilots grieve the loss of the best we had, especially in power dives, lived with the knowledge that Virden had died testing an experimental aircraft, pushing boundaries so that production pilots would have safer machines. The dozens of pilots who died in compressibility-related training accidents, their names recorded in accident reports but rarely appearing in historical accounts, represented the hidden cost of developing revolutionary technology under wartime pressure. Tony Levier, who risked his life repeatedly testing dive recovery flaps and then demonstrated them to combat pilots throughout Europe, survived the war and continued testing experimental aircraft for Lockheed until retirement, living until 1998 and leaving behind a legacy as one of aviation's most accomplished test pilots. Kelly Johnson, whose 1937 warnings about compressibility were vindicated by Virden's death 4 years later, whose engineering team developed the dive recovery flap solution, whose career would span 5 decades and produce some of aviation history's most extraordinary aircraft, would later describe the P-38 compressibility problem as one of the most frustrating episodes of his professional life, not because the technical challenge was insurmountable, but because institutional obstacles and bureaucratic timidity delayed the solution so long. The story that began with Ralph Virden's P-38 tumbling from the California sky in November 1941, the tail separating, the aircraft plunging toward the ground while horrified spectators watched, reached its resolution in the skies over Europe and the Pacific in 1944 and 1945, when P-38s equipped with small hinged panels under their wings pursued enemy fighters through dives that would have been fatal 3 years earlier. The dive recovery flaps, products of wind tunnel testing that NACA initially refused to conduct, of dangerous test flights by pilots willing to risk their lives evaluating experimental modifications, of engineering innovation under impossible wartime pressure, transformed the P-38 from an aircraft with a potentially fatal limitation into a fighter that German and Japanese pilots learned to fear. The modification was not magic, not revolutionary, not based on secret technology or exotic materials, just small metal panels that deployed to shift aerodynamic forces, elegantly simple in concept, but requiring years of research, testing, and validation to develop and field. The civilian engineers at Lockheed, working in partnership with test pilots who understood both the technical requirements and the human stakes, had solved a problem that killed pilots and threatened an entire aircraft program, demonstrating that incremental innovation properly applied could be as valuable as revolutionary breakthroughs. The contrast between German investment in jet fighters and swept-wing research versus American focus on practical improvements to existing designs illustrated different approaches to wartime technology development, Germany pursuing fundamental advances that might win the war if developed in time, America implementing modifications that improved combat effectiveness immediately. Neither approach was inherently superior, but in the context of 1943-1945, when time was measured in months and combat losses were measured daily, American incremental innovation delivered results faster than German revolutionary research, and that timing difference affected outcomes. The legacy of the P-38 dive recovery flap program extends into modern aviation in ways that are fundamental but often unrecognized. Every high-performance aircraft flying today incorporates design features and control systems developed from lessons learned when the Lightning encountered compressibility, when test pilots like Levier and Burcham risked their lives evaluating solutions, when engineers like Kelly Johnson insisted that problems be solved properly rather than ignored. The wind tunnel facilities that NACA eventually operated at high speeds after General Arnold's direct order became the foundation for transonic and supersonic research that made possible the X-1, the first aircraft, to exceed the speed of sound in level flight in 1947, and every subsequent high-speed aircraft. the systematic approach to identifying aerodynamic problems, conducting research to understand root causes, developing engineering solutions, and validating them through rigorous testing became standard practice for aircraft development. But that methodology was refined through programs like the P-38 compressibility effort, where failure meant dead pilots and lost aircraft. The institutional lessons about the importance of research agencies serving operational requirements, about the need for wind tunnels and testing facilities to be available for urgent wartime needs, about balancing equipment protection with mission accomplishment, these were learned at the cost of delays that killed pilots who could have been saved. The recognition that test pilots were not just demonstrators, but essential participants in development programs, providing feedback that engineers could not obtain any other way, risking their lives to validate modifications under realistic conditions, elevated the profession and established protocols that continue today. The photograph of Ralph Virden that appeared in newspapers after his death in November 1941, showing a confident pilot in leather jacket, the caption describing him as Lockheed's best, became a memorial to all the pilots who died developing the technology that others would take into combat. The crash site in Glendale, where homeowner Jack Jensen tried desperately to pull Virden from the burning wreckage, became part of the hidden geography of aviation development, the places where test pilots died pushing boundaries so that operational pilots would have safer, more capable aircraft. The 200 dive recovery flap kits that went down with the C-54 shot down by friendly fire in March 1944 represented not just destroyed equipment, but lost time, lost opportunity, pilots who died in the months before replacement kits could be manufactured and shipped, the cumulative cost of mistakes and delays. Tony Levier's demonstration dives at bases throughout England and Italy in 1944, performing manoeuvres that would have killed him in an unmodified P-38, convinced skeptical combat pilots that the dive recovery flaps worked, that they could trust their aircraft, that tactical limitations they had accepted for months were now eliminated. The confidence that came from knowing their fighters would not betray them during high-speed dives allowed P-38 pilots to exploit the Lightning's considerable strengths, to press attacks aggressively, to pursue targets through any escape maneuver, changing the psychological dynamic of aerial combat. German pilots who had survived months of combat by diving away when engaged by P-38s suddenly discovered that their reliable escape technique no longer worked, that American fighters were following them through dives, that the tactical situation had shifted fundamentally. November 5, 1941, Ralph Virden pushed his P-38 into a dive that would kill him, demonstrating that the compressibility problem Kelly Johnson had warned about 3 years earlier was real, was deadly, was an existential threat to the entire Lightning program. June 1944, P-38s equipped with dive recovery flaps pursued German fighters through the same kind of high-speed dives that had killed Virden, pilots maintaining full control, pressing attacks, achieving victories that would have been impossible 3 years earlier. The transformation from a fatal flaw to a solved problem required wind tunnel testing that government researchers initially refused to conduct, required test flights by pilots willing to risk their lives, required engineering innovation under wartime pressure, required overcoming bureaucratic obstacles and recovering from tragic setbacks. The story was not one of overnight breakthroughs or revolutionary insights, but of systematic problem-solving, of persistent engineers and courageous test pilots, of incremental improvements that accumulated into fundamental capability enhancement. The dive recovery flaps, small hinged panels measuring approximately 2 feet long, made the P-38 Lightning untouchable, not because they eliminated compressibility, but because they provided pilots with control authority when it mattered most, allowed aggressive tactics that had been suicidal, restored confidence that had been eroded by deaths and limitations. The civilian engineers at Lockheed, the test pilots who validated their solutions, the production workers who built modification kits, the maintenance crews who installed them, all contributed to transforming a potentially fatal limitation into a solved problem, demonstrating that wartime technology development succeeded through collaboration between military requirements and civilian innovation. The cost was measured in years of delays, in pilots who died before the solution could be fielded, in missions that failed because tactical limitations persisted too long. But the ultimate success validated the approach and established principles that continue shaping aviation development 7 decades later.